What number do you think I've drawn here? If your answer was 7, you'd be correct. But how does a machine know this? And no, it isn't magic. It's simply maths based on biology. In this video, we're going to build the structure of an artificial neural network layer by layer, uncovering the roles of weights and biases and understanding the first step, forward propagation. You need this understanding to grasp any deep learning model, particularly AI. So let's get building. This network's government name is the multi-layer perceptron, which sounds like something from Transformers, so we'll just call it an ANN. This network has 3 layers. The information comes in the input layer, it's processed by the hidden layer, and the output layer makes a guess on the correct answer. We will be training this model to be a hand-drawn number interpreter. This dodgy image of a 7, which the machine could easily mistake for a 1, is 12 pixels tall and 12 pixels wide, which would equal 144 pixels total. Therefore, the input layer has 144 neurons total, 1 for each pixel in the image. Each of these neurons are given a value between 0 and 1, as most things are with computers. In this example, the value represents the grayscale rating of each pixel. If we were to handpick a pixel from inside the hand-drawn 7, the value would be 0. Whereas a pixel in the corner, its value would be 1. It's important to note that in a better drawn example, all of the pixels would range from 0 to 1, rather than being purely 0 or 1. The pixels surrounding the number 7 may have a gradient which is slightly on the darker side. For example, this pixel here could have a value of 0.23, let's say, because it isn't entirely black, nor is it entirely white. So each of these pixels out of the 144 would have a range from 0 to 1, looking something like this. The end goal of this model is to determine which number between 1 and 10 the hand-drawn image represents, which in this case is 7. This is what the output layer's job is. So, how on earth does the machine make an accurate guess based on 144 random decimal numbers? We're breaking down how the data flows from start to finish, called forward propagation. To do this, let's zoom in on the most fundamental part, a singular neuron. Here we have a singular neuron from the input layer, and its role is to determine whether the 144 inputs suggest a 7 or something else. The number of hidden layer neurons is dependent on the programming and type of model. In this example, we'll have 2 hidden layers, each with 10 neurons. For the second hidden layer, each of these neurons will have 10 connections and 10 inputs from each of the neurons in the first hidden layer. This can be pretty overwhelming at first, so let's rewind a bit. This is the simplest neural network, and parameters are a staple of all of them. A parameter is just fancy computer language for a variable, and there are 2 that you need to be aware of in an artificial neural network. These are called weights and biases, and there are an obscene amount of them. There are many more types of parameters in more advanced models, like transformers, which are the basis of ChatGPTs and LLMs. The most recent form of ChatGPT, ChatGPT 5, is estimated to have around 2 to 5 trillion of them. This highlights the edge that computers and the machine mind have over the human mind: speed. Being the narcissistic species that we are, we based the machine mind on the human mind. There's no wonder it works so perfectly. So, let's use the brain cell, which is a human neuron, to explain weights and biases. The connection between 2 neurons is called a synapse. This is where chemical signals and messages are sent between neurons. These messages are called neurotransmitters. Put simply, a neuron only fires when it receives a sufficient amount of neurotransmitter information from other neurons. For example, if there are only a tiny amount of a certain neurotransmitter in the synaptic cleft, nothing is happening to the next neuron. However, add a few more, and then there is enough of a stimulus to activate the next neuron. Once this certain threshold is reached, the neuron fires, sending its signal onwards. The strength of this synaptic connection can be compared to the weight parameter in an artificial neural network. In a machine, the weight is a numerical value that represents the strength or importance that an input has in activating the next neuron. A high weight means pay attention to this neuron in the previous layer, whereas a low weight says ignore it, this isn't important. When a human neuron fires, the process is called an action potential. There needs to be enough input of neurotransmitters. This is called an action potential threshold, the minimum amount of stimulus which is required for the previous neuron to activate the next. In an artificial neural network, this threshold is what a bias represents. It is a randomly initialized variable in the programming of a network which determines how much total input is required for that neuron to activate. Think of a bias as the neuron's mood. When it's in a good mood and happy, it takes less positive stimulus to make it fire. Whereas if it's in a bad mood, regardless of how strong the weights are, it's going to need a hell of a lot of encouragement for it to fire. Together, weights and biases control how information flows through an artificial neural network, with weights scaling the strength and importance, and the bias adjusting the activation threshold. I was running out of breath there. Both parameters are randomly initialized numerical values at the start of a model's lifespan, or when it's programmed. In this video, we don't need to concern ourselves too much with why, but just think of them as adjustable parameters in the learning phase of the model, as ANN and deep learning models in general learn from data. So, what exactly happens inside the hidden layer? The answer is matrix multiplication, and it calculates the weighted sum of all 144 inputs. To illustrate, we'll use 3 neurons with 3 inputs and 3 randomly assigned weights. To begin the formula for the weighted sum, we take each input and multiply it by its own assigned weight. For number 1, we have the grayscale input from the input layer of 0.76. Its randomly assigned weight is 0.8, so we multiply these two values. This is the same for neuron 2 and neuron 3, and this is also done for all 144. All of these calculations are summed up. So this would be done 144 times for each input times its weight, but for these examples here, the result of the first one would be added to the next. This would then be added to the next, and this continues. After this summation is complete, we finally add the neuron's mood, which in this case is slightly above average, 0.1. The result of this calculation, which is Z, is a single powerful number which sums up the whole neuron's thought process from its 144 inputs in the previous layer. This Z-score is then ready to be passed on to the next hidden layer. Each neuron receiving inputs throughout the whole model has this weighted sum formula applied to it. So this is an example of one of our neurons in hidden layer 1. If it was the second neuron in the hidden layer, its bias will be completely different. For example, 20, which is a large difference to the 0.1 in the first neuron. Neuron 3 might have a -5 bias, so you can see how these weighted sum calculations would be different, although the inputs are the same. But we're not done yet. As clever as this all is, the simple linear math creates one major flaw. If we only use the weighted sum, which is just linear math, we can solve some basic problems. Let's say our network is trying to tell the difference between green data and red data. In this case, a straight line, which is linear math, is perfectly fine. We can have single decision boundaries, which can cleanly separate between the two classes of data. But complex patterns and the real world are rarely this simple. This complexity is shown by the XOR pattern. These red points belong to one class and the green points belong to another. However, they are arranged diagonally in a non-linear way. No matter how I draw a straight line, which is linear math and a linear function, we can't separate the 2 points. See, we have both on either side here, here, here. It becomes very difficult. Complex relationships are impossible to learn this way. Your brain faces the same problem when identifying a handwritten digit. A 7 isn't just one straight edge, it's a combination of curved lines and edges that your brain summarizes as a whole and determines is a 7 rather than a 1. So, how does the network solve this failure? It solves it by using an activation function. This activation function converts the linear weighted sum and bends the math so it creates a non-linear function. Because the math is bent, the network is no longer restricted to straight lines. It gains the ability to draw a curved decision boundary, which, as you can see, has isolated the two classes of data. This non-linearity allows the network to combine single inputs into complex relationships, just like your brain does when recognizing the number 7. Now, the curved line we drew on the XOR problem was just an arbitrary decision boundary, a visual example to explain why we need non-linearity. In reality, the specific activation function used is commonly the sigmoid function. This is its shape. It combines the neuron's weighted sum input and compresses it into a function between 0 and 1 in an S shape. This makes it possible for the network to build complex decision boundaries. More about this in the next video and why it's essential for the network to learn. For now, let's combine everything that we've learned in this video, displaying the ANN structure and describing forward propagation from start to finish. So, we start with the hand-drawn image of a 7. This has 144 pixels total, so the input layer has 144 neurons. Each of these neurons has a grayscale rating between 0 and 1, 0 being completely black and 1 being completely white. Next, we have the first hidden layer, which we initialized with 10 neurons. We would take the weighted sum from all 144 neurons and pixels, which is each neuron times by their specific weight, and then added up 144 times, the better word for that being summation. We then add the specific bias that this neuron has been assigned. We take this total weighted opinion that this neuron has gained from each of the neurons in the previous layer. We apply the sigmoid activation function to introduce non-linearity, and then the output and value of this neuron, and that it will hold and progress, is between 0 and 1. Remember, this step applies to each of the 10 neurons in hidden layer 1, which each have their own randomly assigned bias. Each of these 10 hidden layer 1 neurons hold a distinct value between 0 and 1, all having their opinions on their inputs beforehand. Now, all of these new values that each of the 10 hidden layer 1 neurons have are used as inputs for the weighted sum calculation. All of these connections have new weights. If we were to do the weighted sum calculation for this neuron here, this neuron has its own bias, which could be anything. The bias of this specific hidden layer 2 neuron, which has just had input of the weighted sum from the previous 10 inputs before, then gets added on. The sigmoid of function is applied all the same, and then this neuron gets a value between 0 and 1. Again, this process will occur with each of the hidden layer 2 neurons, and they all develop their own value and opinionated score of the whole prior network between 0 and 1. The exact same process of the last 2 layers is applied again, and, as you may have guessed, there are new weights and new biases involved. Forward propagation is complete. The network has generated its final confidence scores. It'll look at the highest score and give us its prediction. Let's see what it comes up with. And after all our hard work and learning, along with the machines, all of it is about to pay off. As we can already tell, the answer is a 1? Are you having a laugh? I must have been learning the wrong thing. The network is wrong. We fed it a 7 and it's certain that it saw a 1. Here is the unfortunate truth. We are only halfway there, which is why I'm very glad I've decided to break this up into 2 videos. That would have taken a while. Our network currently has all the hardware it needs, all the weights, all the biases, the sigmoid function, each layer, but it has no experience. Its brain is empty. It's just been born. The 1,670 total weights and biases that we gave the network were randomly initialized. That's why it failed. We need a way to take this error and send it back through the network, telling each weight exactly where it messed up. This astounding discovery, which allows the network to learn, is called backpropagation. And this is what we will be tackling in the next video. Let's leave it there for now. As always, thanks for watching. If you learned something new in this video, please consider liking the video and subscribing to the channel so you can follow me in learning and understanding this new apocalypse. Well, hopefully not apocalypse, but potential insane growth and domination that AI will have in the world. Thanks again, and I'll see you in the next video. Stay tuned.